Hey, good afternoon, everybody. Welcome back. Uh, let's see. If you guys noticed, I posted a few things online, so you can jump onto Canvas and download those. We'll start off with a few announcements. Let's see what I got here. That's the other class. All right. Did you? Always seems like I'm got a few extra things I need to do before. There we go. Now let's get back to Zoom. Share the screen. All right. Okay, so today's Thursday, August 31st, and this is lecture number 4. No office hours tomorrow. Had a couple visitors this morning. When we look at our schedule for next week, remember Monday is Labor Day. That doesn't really affect us in this class too much, but it's going to be a nice day for me to get caught up on some work. So I'll keep my office hours basically the same next week, 12:30 to 2 on Wednesday, and then 8:30 to 10 a.m. on Thursday. Let's see, what else do we have here? We have no TA assigned for the class yet. That's still an annoyance for me. Excuse me, for me and some of my colleagues. We're still waiting to see who's going to be grading for this class. Interesting question. All right, we have homework number 1. I told you last class that I would move it by a day, but then I thought, well, it doesn't seem appropriate to make it due on a Friday before a long weekend. So I moved it to Tuesday after the weekend. So it's technically due Tuesday, September 5th at 5 p.m. Then I posted homework number 2 this morning, and that's a beam modeling exercise in visual analysis first, and then in SAP 2000. It kind of mirrors what we're doing with our demonstrations here in class. When I made up this slide, I said not before Tuesday 9/12, and then when I posted the assignment, I think I made it due on September 12th, but that could slide a day or maybe 2 without too much problem. It's an interesting assignment. If we look at the what I'm asking you to report for the assignment, it's not terribly complicated to create the models. To create a model in visual analysis with the loads that I have stipulated, to create a model in SAP 2000 with the loads that I have stipulated, probably won't take you more than 45 minutes for each of the 2 things. Regrettably, reporting the output will probably take you twice as long as creating the model. So it seems like that's often the way things work out when we start to look at these modeling problems. It's not so bad to create the models and to do the analysis and get results, but sorting through the results and reporting them in a way that you and your coworkers can understand is challenging. So I expect that the PDF that you would submit there is going to be on the order of 20 to 30 pages long. But a lot of it is probably just going to be screen snipping and pasting. So for example, here's my solution to this assignment. So, here's problem 1A where I'm reporting some reactions. I've just pulled those out one number at a time and put them into an Excel sheet so they look nice. And so your TA and your instructor don't go insane when they grade it. When it comes to moment diagrams and moment envelopes, I've just taken screenshots or screen snips or whatever and pasted those in. The only requirement is that we have to be able to read the numbers, so make sure that you're legible when you do that. And you can do the same thing in SAP 2000. I don't want to give you all the answers, so I'll just give you that and let you know that you don't have to spend hours and hours outputting tables of results and then creating brand new shear force and bending moment diagrams from Excel or something like that. So bigger picture, what I'm going to do is ask you to complete this assignment, and getting the results out of visual analysis in SAP kind of sucks. Doesn't kind of suck. It really does suck. And then after you guys do this, I'll show you an easier way to get the results out. And so then in the future, you can dump your results to an Excel file directly from either visual analysis or from SAP 2000, and you can do some manipulations there. Shear force and bending moment diagrams are tedious in any case. So if you're gonna draw them in Excel, it's still tedious, even if you know how to do it directly. But all right, so that's my my thought process. So when you guys dive into this and you start actually doing the work, you're going to say, well, shit, this is a lot of work. And I just want you to know, yes, I know I'm there with you. It sucks. But you know, it's kind of like doing everything the hard way first makes you appreciate doing it the easier way later. So that's my thought process. All right, then we're going to spend some time with this bridge again today. So one of the things that I wanted to show you was that I added a slide here that shows you what a truck loading is. We're going to put this HS20 truck load on that bridge girder that we modeled last time. And so I had to define what that is. It's basically a truck with the axle loads of 8 kips for the front axle, 32 kips for the rear tractor axle, and 32 kips for the trailer axle, with axle spacings shown as 14 and anywhere between 14 and 30. So some of you haven't had bridge engineering. Some of you might not have covered this in your loads and systems class. So we need this definition in order to move forward. Before we do that, though, I wanted to spend a moment and talk about the homework assignment for the class. I told you last time that I would spend a few minutes doing that. So let's go ahead and do that. Hopefully problem number 1 isn't too challenging. You just draw some arrows on here representing the displacements delta X and delta Y at every node. Number those displacements and you're good to go. And then same thing for problem number 2 if it were modeled as a frame instead of as a truss. So when we look at problem number 3, this is probably still intuitive, but I'm going to go ahead and do a little bit of tutorial on this just to make sure we're all on the same page. I see a chat. Let's see what's homework number 2 assignment is posted, but the PDF file is not linked or accessible. Okay, thank you, Joe. I'll take a look at that after class. Yeah, and if it hasn't been fixed by like 4 o'clock, you know, message me and let me know, and I'll probably remember, but you know how I am sometimes. So. All right, so what I have in mind for that, I think I actually have a template for that too. Let me bring that up and see what that looks like. Yeah, so here we go. So here are the nodes for problem number 3, and here are the solutions for problem number 4, and then problem number 5 is an open blank. So what you might do is you might go in and say that for node number 1, that's at X equals 0 and Y equals 0 in terms of feet. Over here, I might just use an equation and say it's equal to that times 12 to convert to inches. So that's fairly straightforward, I think. Let me go ahead and do node number 5 as an example as well. So that's at X equals 20 feet and Y equals 16 feet. So if I go up and, whoops, bring that down here. So I have those 2 nodes. Okay, let's see. What is problem number 4? Create a spreadsheet with 1 row and 1 number, right? Blah, 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 blah. Right, okay, so this is going to have a row for every member. There are 7 members in this guy. And so what I'm going to do is let's take member number 2 as an example. So this connects node number 1 and node number 5. And so what you want to do is calculate the length of this guy. And so there's a number of ways you can do that. Let me introduce you to the VLOOKUP function if you don't already know what that function is. So what I want to do is I want to set the length equal to the square root of the sum of the squares. So it's basically going to be the sum square root of, let's see, the jth value. Let's see, we'll do this. X sub j minus x sub I squared plus y sub j minus y sub I squared, where in this case, x sub j and x sub I are the x coordinates of the jth node and the ith node, respectively. So if member 2 goes from node 1 to node 5, then the ith node is node number 1 and the jth node is node number 2. Let me do that. I'll make it a little bit bigger so you can actually see. Then I'll go and do that again. All right, now I don't have xj, xi, yj, yi defined. What I have to do is go back here and look up those values. So this is x sub j. This is this is x sub I. This is x sub j. So what I can do is use a VLOOKUP function in there. So let me do this and say VLOOKUP. I want to look up the x value of this node number in this table, and I want to use the 1, 2, 3, fourth column. So I'll go ahead and hit comma 4, comma 0, and then close that out. And so then I'll go through and use dollar signs on that to make it an absolute reference. Now it's still giving me errors, so I need to do the same thing for x sub j. So let me copy that. All right, there's x sub I actually. And so now this time, let's see, we'll get that backwards. So this is actually, I want D6 and C6. Now let's do the values for I. So I'm going to copy that function again. There's y sub j. Except now I want the fifth column of that table. And then I'll do this, copy that. And here I want the fifth column of that table. So then I can go through and it calculates 307.3 inches as the length. So what the VLOOKUP function is doing is it's going through and looking up a value in the table on the previous sheet. It's looking up the value of x sub j and x sub I. So if I included those as in their own cell like this, so if I go here and say I want this equal to that, it's going to look up the x value of node number 5. And so if we go back here for node number 5, the x value is 240. So I could go here and type in node number 1. It looks up the x value of node number 1. So it's just a dynamic way of looking up those node values. Now, if you wanted to, you could insert some cells here and put in x for the first node, x for the second node, y for the first node, y for the second node. But that's far less dynamic and far less educational. So if you don't know what the VLOOKUP function is, you're probably thinking, well, gee, this seems really complicated. After you realize how useful it is, you'll thank me. You can send cards to my home address, preferably with a check involved, and everybody will be happier, including me. All right, next step is to calculate the directional cosines. I don't know if you guys remember, but this was the last slide of our modeling tutorial. So let me open that PowerPoint. I'll just bring it over here like that. And I guess it wasn't the last slide. Here it is, near the last slide. So the directional cosine of phi is the angle of orientation of a member within space. So we can calculate cosine of phi, or we just call it C as shorthand. We can calculate the sine of phi, we just call that S in shorthand. So basically it's x sub j minus x sub I divided by the length, or it's y sub j minus y sub I divided by the length. So I'll assume that you guys can go through and enter those into your spreadsheet appropriately, knowing now what you know. So, right. Okay. Well, let's go ahead and do it just to be on the safe side. So let me copy that function. I'm going to paste it in over here. Then I'm going to modify it. So I don't need a square root. So let me get rid of that. I'm going to get rid of that parens. I'm going to take x sub j minus x sub I divided by the length. So I take that. Now I divide by the length. Whoops, I need an equal sign. And that ain't right. Let's see. Divide by length. I don't know why that didn't work. There we go. There we go, 0.7809. And that it always has to be between 0 and 1. So if you get a number that's negative, it's wrong. Actually, no, it could be negative. It can be between -1 and +1. So if you get a number bigger than 1 or smaller than -1, then you know for sure that the answer is wrong. And so then we do the same thing for the directional cosine. All right, now the rest of that homework assignment, let me close that. I no longer need that. Go back here, is matrix operations. So there's a lot of ways of doing these matrix operations. And so let me show you some examples. So we just want to do just matrix addition. So let me just come up with some hypothetical matrices. Oops. And let me go over here. Damn it. Make that an 8 then. There we go. So if this is the matrix B and this is the matrix A, then we can make matrix C. A couple of ways of doing that. You can say this is equal to 2 times that plus this. And then you just copy that down and you get a matrix result. I copied too many rows. All right, so that's relatively straightforward. I think you can actually do it on an array form as well. I think you can say, I'm not going to try that because I'm not positive. Let me show you another example here where we multiply two matrices together. So let me take A times B and put it in this slot here. So what I'm going to do is select a 3 by 3 group of cells, because if you multiply a 3 by 3 by a 3 by 3, you should get a 3 by 3 resultant. So I'm going to use equals MMULT, and that stands for matrix multiplication. And then I'm going to put a parens, and I'm going to select matrix A as my first array, comma, matrix B as my second array. I'll close the parens, and then I'm going to use Control-Shift-Enter when I close that out, and I get that. Lovely.
The value selected for matrix A was larger than the actual matrix.
Oh, did I select too many? Okay. Let me do it again. Thank you. Equals MMULT. Okay, and then, whoops, close that. There we go. Thank you, Joe. Appreciate it. So that's the way you do matrix multiplication. You can also do transverse as well. So we can do a transverse of a matrix. So this is equal to transpose. I said transverse, transpose. Sorry. So then you can do that. Hit Control-Shift-Enter. It gives you the transpose of the matrix. You can also do the transpose of a matrix multiplication. So we can embed these. So MMULT, and I'll put that one, do it right this time, put that one, close that, hit Control-Shift-Enter. It gives you the transpose of the matrix. So you can embed those as well. Now, if you want to do the last one where you have K times delta equals P, what you're going to do is end up with delta equal to K inverse times P. Hopefully you guys recall this from your math classes. So what we can do is I can go here and take the inverse of A, and I'll select those 3 by 3 array of cells. I'll type equals MINVERSE, M inverse, and do that, and then hit Control-Shift-Enter, and it gives me the inverse of that matrix. Okay, I can embed those as well. So I could say that this equals MMULT of the M inverse of this guy as my first array. Whoops, I need a closing parens, then a comma, and then I could take that as my second, and then I hit Control-Shift-In, and it didn't give me, I didn't select the right number of cells to begin with. I don't think I can do that. No, I can't. So let's see. Let me copy that, delete that. There we go. And so you can embed those operations as well. So why are we doing matrix operations? Well, the reason is because we're going to do the matrix solution to some of the problems. And I like to do that in Excel where you can see all the operations. Yes, you can do it in MATLAB, probably easier, but I don't think that MATLAB is as transparent in how it's going through. I like to see everything broken out to where you can see one matrix, the other matrix, the product of the two. And so that's why I like to work in Excel. I concede that it's clunkier and less elegant than MATLAB would be, but I think for learning the process, I think that it has utility. So that's why we do that. All right, questions about this? All right, then let's go ahead and I'll close that out without saving. No. And then we'll move on. Oops, I still need that. Oops, not that, that. All right, so we did some work last time creating beam models for SAP 2000 and visual analysis. What I want to do is expand on that a little bit. Lean back here a little bit, get more comfortable. Bring the mic closer. There we go. Now, there, perfect. All right, so we're going to reconsider the 36-231 in the Indian River Bridge. We're going to strengthen the girders by adding cover plates. So if we go back to this slide here, then what you'll see is that there are moment plates that are included in our design. So we have a top plate 15 by 5/8 by 14.5, a bottom plate that is 18 by 11/16 by 14.5. So what we want to do is add those on. So that's what I'm saying here. Top cover plate is going to be 15 by 5/8. It's spanning 7.5 feet from either side of the support. Not entirely consistent with what the drawing said, but close enough. And then we have a bottom cover plate 18 by 11/16. So it's common when you have cover plates to make the cover plate on the top narrower than the top flange and the cover plate on the bottom a little wider than the top flange. And the reason for that is it makes the welding easier. So you don't have to weld in an overhead position. Right. And then we're going to also add hinges to the girders 15 feet to the right of support B, 15 feet to the left of support C. And then finally, we're going to add a HS20 truck live load and include some load combinations. So that's the goal of today's exercise. So what I'll do is go ahead and start with SAP 2000 today. We started with visual analysis last time. I'm probably going to run out of time before I get through both of them. And I just like SAP better. So let's work in SAP first, and then we can spend some time in visual analysis later. Takes a minute to launch on this machine. Still taking a minute to launch. It's conspicuous. There it is, finally. Conspicuously long. All right, there we go. Okay, so I'm going to go ahead and load the model that we worked with last time. It has, what did I call it? XYZ? I think I did. All right, so there's the model that we had last time. So I want to do a few different things. One, I want to add the cover plates. Two, I want to add the hinges. And three, I want to add the truckload. Let's go ahead and add the cover plates first. I think that's what's covered first if we look at the tutorial. So yeah. So in order to add the cover plates to this model, I'm going to go ahead and first thing I'm going to do is hide the grid. And if we go up here to the view, you can display the grid or show the grid. So I'm going to just hide the grid. And maybe that's a little cleaner for the work we're doing right now. So I can go ahead and show the restraints. That kind of gives me a little bit of a, let's see, for nodes, I want to show the restraints, hit apply. There we go. So in order to add the cover plates, I need to change the cross section that we're working with. So you can't have two different sections applied to the same member. So I've got one member, one line object defined between node 1 and node 2. So I need to split that into two line objects in the model, and then I can change the section properties that are associated with one of those two line objects. So what I'm going to do is I'm going to split this member into two, and I want that split to occur 7.5 feet to the left of node number 2. So that element is 60 feet long, and if I subtract 7.5 feet from that, that means the first element's going to be 52.5 feet long, and the second element's going to be 7.5 feet long. So what I'm going to do is I'm going to go up here to the edit menu, and I'm going to go to edit lines, and then I'm going to divide it. But I have to unlock the model first. I ran the model at the end of class last time, and whenever you run a model, it creates results, and it locks the model and keeps you from editing it, so that the model that you have defined in front of you is consistent with the results that it has calculated. So I'm going to go up and click on this padlock, and that's going to unlock the model, and it's going to allow me to edit it again. But when I do that, it's going to delete all of the results, because when I make changes to the model, the results that I had are no longer relevant. So that's one way of idiot proofing the software that SAP does. So I'm going to unlock the model, and that deletes all of the results that I had. Now I'm going to select that member again. I'm going to go in here, edit lines, and I'm going to divide that frame. It's a frame object is why it says edit frames. And so that gives me this dialog box. It's rather busy, but you'll learn to appreciate that because it gives you several different options. I can either break it into a specific number of frames and then define the ratio of the first one to the second one. I can break at intersections with other nodes, frames, or edges, or I could divide the frame at a specific distance. And so at this point, I want to specify an absolute distance, and I want that to be 52.5 feet from the first end. So I put in 52.5, I hit the caret, I tab out of that, it changed to feet right there, and now I hit apply, and you can see that it put a node in there. Now, if you want to make sure that that is actually two different frames, what you can do is go to the display options. Whoops, I hit Windows W instead of Control W. And you can go to the general options, and you can look at a shrink objects view. And so what that does is that shrinks each of those frame objects so that you know which nodes they attach to. So in this case, you know this first object here isn't going over node 5 to node 3. And so that shrink objects can be helpful for that. All right, let's hit apply. Get rid of that. Let me go over here. In this case, for the last element, what I want to do is go ahead and edit lines again. I can come up here. In this case, I want an absolute distance of 7.5 feet instead, because I'm measuring the distance from the first node to the second node. And when I drew that beam in, I drew it from left to right. So I'll put in 7.5 feet there like that, and you see that node pops up. Okay, now this middle one's a little bit trickier. That has a length of 75 feet. So if I take 75 feet and subtract 7.5 feet, that gets me 67.5 feet. So I'm going to go ahead and break it first at 67.5 feet like that. That creates that node. Now I'm going to go back and select that again, and I'm going to type 7.5 feet instead. And so now I have those nodes like that. All right, now let me close that window out. I can go back here to the shrink view again, and you can see all of those line objects, all those frame objects connect to just their adjacent nodes. Now you might question, why don't I just have one frame object spanning from node 5 to node 9? Well, the answer is that in order to have a restraint there, I have to have a node there as well. You have to have a node everywhere where there's a restraint. You can't have a restraint without having a node. So that's why that's there. Okay, so let me go ahead and look at the section that's applied to each one of these. So when I split these members up, it took the section that was originally I created an extra node over here. Let's see, how did I do that? I must have had that member selected when I split this other one up. I probably had two members selected at the same time. I want to get rid of that. I want to join these two frames back together. I'm going to go here, edit lines, and join those two frames. And there, now that's gone again. Okay, good. All right, now when I split these members up, it just kept the same section properties. But now I know that the section properties are going to change for these elements here and for these elements there. And so the section properties that I'm going to assign are at the end of this PDF. You can see I've done some homework here. And so we have the moment of inertia, the cross-sectional area that are defined. So the moment of inertia that I want is 23,070 inches to the fourth. The other properties aren't terribly important. So let me go ahead and put those values in. What I'm going to do is select those four members or those four frame objects. I'm going to go up to assign frame. I want to go to frame sections. I don't have that new one defined yet. I could define it here. And so what I want to do is add a new property, and I'm just going to create a general property. So I'm going to call it other, and then I'm going to go in here to general, and now I can put in those section properties explicitly. Okay, I'm working in units of feet though. I should have changed that to inches, but let's go ahead and do this. Let's see, I've got 23,070 inches to the fourth. Let's see if it changes. No, it does not. Let's see, 23,070 inches. Okay, that worked. 23,070 inches again. I'm just going to change both of those moments of inertia. I haven't talked about local coordinates yet. So one of them is a weak axis moment of inertia. The other one's a strong axis moment of inertia. And just to make sure I get the right one, I'm going to change them both. Okay, let me go to OK. We'll call that W36X231 with CP with cover plates. I'll hit OK, and then I'll hit OK again. Now I'll select that. I'll hit apply. And now you can see it changes that. All right, let's see what happens if I go down and change my units to kip inches instead. Let me go back to this. I'll define that section again. I'll go ahead and modify and show the properties. Let me go ahead and see what the section properties are. And yeah, so it changed it to 23,070 inches to the fourth. Okay, I just wanted to double check and make sure it did that inch to feet conversion properly. All right, now the next thing that I want to do is add nodes releases into the model. So let me go back to the top of the PDF. I want to add in, let's see, I want to add in a hinge 15 feet to the right of support B. I want to add in a hinge 15 feet to the left of support C. So what I want to do is put a hinge in right about there. And I want to put a hinge in right about there as well. Now, like restraints, in order to put a release in, we have to have a node in the model at the point where we want the release. So I need to split this member up again. Let me select it. There we go. So I'm going to go in here. I'm going to go edit frames again. That member, let's see. Let me go ahead and right click on that member. It should give me the length in here someplace. I guess it doesn't. Yeah, it is 720 inches. Let's see what that is in feet. That's 60 feet. So that frame is 60 feet long. So what I want to do is split it 7.5 feet from the right end and 7.5 feet from the left end. So we're going to go to edit lines, divide frames. I'll start absolute distance. See if I take 60 feet minus 7.5 feet. Let's do it this way. So 60 minus 7.5 gives me 52.5. Let me type feet in. That gives me 630 inches. I'll hit apply. And God willing, that should have given me another hinge there. Yep. All right, let me do the same thing here, and I'll split that now 7.5 feet from the left end hit apply, and there, now we have those hinges there. All right, now I'm going to get rid of the shrink view. Hit Control W, get rid of the shrink objects. Let's get rid of the sections now as well. They're getting kind of cluttered. Hit apply. Hit apply again. All right, let's refresh the view. If we go up here to restore full view, it should have worked. Huh. Why won't that work? Apply. All right, well, I'm not sure why that's not working. I'm going to go into this member here and I'm going to release the moment connectivity at the left end and at the right end. So you go into assign, frame, and releases and partial fixity. And it gives you this busy dialog box. And what I'm going to do is release the moment at the left end and at the right end. I'm going to release the moment at the start and at the end. Now it has M22 and M33. We're not sure yet which one is a strong axis and which one is a weak axis, so I'm just going to release both of them to make sure that I get the right one. If I release the weak axis moment, it doesn't make any difference because we defined this as a 2D frame, so that won't impact the analysis at all. It does tell me there, though, that M33 is the major axis moment and M22 is the minor axis moment. So really, I could do just M33 and be confident that that's okay, but this won't hurt either. So let me hit apply. And when I do that, see that it puts that member into shrink view and then gives me a green dot that shows that that's an indication that there's some sort of release at that point. Okay. So that's the only way that you know that there's a release. If we go and we right click on that member, we can come in here and you can see that it has a release at the ith end, M2 and M3. It has a release at the jth end, M2 and M3. If we go and click on one of these other members and look at the same properties, there are no releases. So if you right click, you basically see a small database of all of the properties associated with whatever object it is that you clicked on. Okay. Now what I want to do is go ahead and create the live load on here. So where is that at? I actually did the live load first in the tutorial before I did the releases. So I want to create live 1, live 2, and live 3. And what that's going to do is allow me to put the live load in span 1, in span 2, and in span 3. So I need to create 3 new load patterns. So let's go up here to define load patterns. Let's go ahead and I'm going to modify this one first. I'm going to call it live 1. I'll hit modify load pattern. I'll go here and say live 2. I'll add a new load pattern. I'll go here live 3 and hit add new load pattern. All right, and so when I create each of these load patterns, it creates a load case for each one of them. I had originally called the first one live. I'd called that L, so I can change that. Let me go ahead and modify that just because I'm anal retentive. So I can modify that now and call it live 1. And as long as we're in here, this is a load case definition. And so this is one of those dialog boxes where some of you guys know what a p-delta analysis is. Some of you guys know what a time history analysis is. Some of you guys don't know what any of that is. But for those of you who are familiar with some of those advanced analysis techniques, here's where you define those. If you wanted to do a multi-step static analysis, if you wanted to do a time history analysis, if you want to do a stage construction analysis, this is where you define all of this stuff. So this is where we're telling SAF 2000 what we want to do with that load pattern. And right now I want to do a static linear analysis with that load pattern. And so that's basically the simplest analysis you can do. It's basically the old CVE 3001 type of an analysis. Let me go ahead and modify that one as well. I'll call it D instead of dead, and then I'm happier, right? This modal analysis, that's where you would get the natural frequency of vibration of the structure, and you could do some more things with that. We're not going to do anything with that, so I'm going to delete that just to keep our workspace a little bit less cluttered. All right, now I need to apply a truckload. And so what I want is a truckload. Let's see, I want it facing to the, let's go back here. Where did I define what I wanted there? I wanted a truckload facing to the right with the center axle in the midspan of span 2. I want a truckload facing to the right with the center axle in span 1 and a truckload with the center axle in span 3. That must be a typo. That should be 3 there, I think. Sorry for that. It's funny. I used the same tutorial last year, and it's probably a typo there as well, and I didn't notice it. All right. So let me do some math here. This member from support to support is 60 feet. So I want the center axle to be 30 feet to the right of the left support. And then if I look at the truckload, let me go here and do that, do that. So that means that I want the rear axle to be 14 feet to the left of the center, and I want the front axle to be 14 feet to the right of center. So let's reason through this. Hello, I'm trying to select that member. I'm not able to click on it, so let me window like that. Oh, this is quirky. I've never seen SAP behave so poorly before. I wonder. There we go. Finally, I guess I just have a lot running on this machine. All right, so let me go to assign. I want to assign frame loads, and I'm going to put point loads on my frame object. Now it allows me to put up to 4 different loads on in the same thing. I'm going to call this live 1 because it's a live load in span number 1. And so I'm going to go ahead and put the loads in at different distances. Right now it's set to give me a relative distance. So if I put in 0.5, it's going to say halfway along the length of that member. I want to put in absolute distances instead. So I want the middle truckload. Let's go ahead and do this. I want the middle truckload at a distance of 30 feet. And I want that middle truckload to have a magnitude of 32 kips. That 32 kips is going to be in the gravity direction, so it's going to be pointing downwards. I want the first load to be at a distance of 30 feet minus 14 feet. So I'll type in 30 minus 14, and then I'll go back and say, okay, really that should be inches. So I type in feet. That first truckload is going to be the rear axle at 32 feet. Then over here, I'm going to type in 30 plus 14. Then I'm going to go back and convert that to inches. And this is going to have a magnitude of 8 kips. So 8 like that. Okay, I think that's right. Let me go. You have an option up here to add to loads that might already be on there, or replace loads or delete loads. I don't have any loads on that member in live load number 1. I have dead loads on there, but they're in a different load pattern, so I'm not going to replace those. Let me hit apply, and you can see how I have those. Now, so this 32 kip load here should be between supported A and B. This should be 14 feet to the right of the middle. This should be 14 feet to the left of the middle. This is a good time to show you something else. What if I'm not sure about the dead load? If I want to see what dead load is displayed, I can go here to show object load assignments. I can go to the frame object, and I can select which load pattern I want to display. I'll hit apply, and it shows that dead load applied to all of them. Now it's a goofy unit, 0.12, and that's because it's in units of kips per inch. If I go to kips per foot, it's 1.45. Okay, if I want to see the live load pattern number 1, I hit apply, and that brings me back to that. All right, let me go through and do this a little bit faster. So this member should have a length of what? Go here to location. That gives me a length of 45 feet. So middle of 45 feet is 22.5 feet. So I'm going to assign frame loads point. Live load pattern number 2, 22.5 feet is 32. This is going to be 22.5 plus 14. I'm working in units of feet now. And this is going to be 22.5 minus 14. Note that it does the arithmetic in the cell for you, which is pretty clever. Visual analysis will do the same thing. All right, so I hit apply, and I get those forces like that. And then now we'll do the same thing over here. Let's see. I want that center point load. That was going to be 60 feet divided by 2, and then I want to subtract off 7.5 feet because I have 7.5 feet at the left end between the support. And so that gives me 22.5 feet. So now I'll go here and I'll say 22.5 plus 14. Here I'll go 22.5 minus, whoopsie, 22.5 minus 14 and hit apply. Ah, shucks, I put them in load pattern number 2 at the same time. So I goofed that up. All right, let me hit the undo button. There we go, and they're gone forever. Now we go to live 3 and select that and hit apply. There we go. And so now we have truckload applied in those 3. All right, now a lot of editing. Let me go ahead and save the model. It won't run the model without saving it. That's a good thing to know. So if you're not sure about something, you need to save it as a different version. So maybe we would have saved it as XYZ02 or something like that. Every time you run the model, it saves the model. So it's good in some respects. It's bad in some respects as well. Yeah, so be careful of that. Go ahead and run it. I want to run all load cases. So let's go ahead and hit enter. And it should give me the deformed load or deformed shape. So this is a deformed shape for load pattern D. I can also show the deformed shape. So I go to display, show deformed shape. And what it does is it lets me select which case I'm working at. So I can show the deformed shape under load case 1. I can show the deformed shape under load case 2. Right, and I can show the deformed shape under load case 3 like that, and see where the kinks are coming in here. That's indicative that I have that pin in there and it's functioning like I want it to. All right, we'll hit close. We'll go to display. We'll go to show forces and stresses. So I can show there's the joint reactions. That's also useful. So there's my reactions for dead load. There's my reactions for live load 2. Right, I'm actually getting a downward force there. I can actually show them tabulated if I want to instead, and that just gives me the reaction for 3. You have 1, 2, and 3. So 3 is the Z direction, so that just gives them tabulated. I like the arrows. The arrows are nice. Right, so that's useful, but that's not what I meant to do. Let's go here to show forces and stresses. There we go for that. So now we can plot the moment diagram M33. There's the moment diagram for dead load. Let's flip it over for those of us that are used to showing the moment diagram for the tension side. Sometimes you have to cycle that button twice. It's a little bit quirky like that. I don't know why, but it's just always been that way. We can show values on this as well. And so you can do a screenshot of this for your homework number 1 and make sure those numbers are big enough. I think if you go and tinker with the preferences, you can make those numbers larger. We can go in and select the moment diagram for live 2. And so there you go. We can select the moment diagram for live 3 if you want as well. Oh, that looks okay because we have a pin there, right? So, yep, that looks good.
Are you limited to adding only 4 point loads per load case?
No, I can add as many point loads as I want, but I can only add 4 at a time. Then you would have to go back and repopulate that dialog box. You can add 454 if you want to, and you'll be just fine. All right, now let's do load combinations. Now, I'm going to define load combinations. I'm going to go in here and click define load combinations, and it's going to allow me to do some work. And note that I didn't unlock the model. Right? So I'm making quote unquote changes to the model without unlocking it. So I'm violating the first commandment of SAP. Well, really, I'm not, because load combinations only deal with the results of an analysis. They don't change the way the model is constructed. They don't change the way the model was analyzed. So if all I'm doing is recombining different results from my run, I can do that without unlocking the model. So let me add a load combination here. I'm going to go back to the PDF and see I'm using the AASHTO strength 1 load combination. So that's 1.2D plus 1.75 times live load plus impact. I just realized a mistake that I made, but I'm going to gloss over. I'll come back and touch on that at the end of the class session. So I'm going to put in here a scale factor 1.25 times the dead load, and I'm going to go in here and I'm going to say live load number 1 with a load factor of 1.75. I add that, and let me call this strength 1 for span 1. All right, so that's the strength 1 load combination applied to the live load when the live load is in span number 1. I'll hit OK. And let me go ahead. I'm going to add a copy of that combination. This is going to be here. Now I want live 2 instead of that. And so let me modify that. And now I'll go up and call this strength 1, str capital 1 dash span 2. Hit OK. Let me add a copy of that one as well. We'll change that live 2 to live 3. Modify. I'll go up here. I'll call that str1 space span 3, like that. All right, I'll hit OK. And now when I go in and plot my moment diagrams, this button here is just a quick tool for getting there. What I see is that I have more options in here. So now I can plot the load combination for the live load in span number 2. And so that gives me the result of 1.2 times the dead load moment diagram plus 1.75 times the live load moment diagram for the live load in span 2. Right, and I can do the same thing here like that. Right, and that's for the live load in span 3. Now, most of the time when we're doing our designs, we often want to know what is the maximum of all of those cases, what is the extreme value. And so what we can do is go and define one more load combination, and I'll make this one an envelope. And so I'll call it up here, ENVLOPE. Got it right. Okay. And so what I want to do is go in, I want to take structure, strength 1, span 1, and I want to add that. I want to take strength 1, span 2, add that, strength 1, span 3, and add that. All of them have a scale factor of 1, but now instead of a linear add, what I'm going to do is select an envelope. Okay? And so what that'll do is that will give me the maximum and minimum value of bending moment and shear force at all of the locations along the length of the member. So let me go back to my plot diagrams window. And so now you can see that I have envelope as an option here. Got to hit apply. And so now you can see I get 2 values at every location along the length of the member. It gives me the max and the min, so it's a multi-value output. And so I get 2 values everywhere. So I get a negative whatever here, I get a positive whatever there. So that's the design envelope for that girder for that series of loadings. All right, now let me show you a few more things. I'm not going to bother launching visual analysis today. These diagrams are nice, but they're not perfect. Let me show you a shear force diagram before I go away from this, though. So I can go in here and plot shear 2, and that's going to give me a shear envelope. I could go into strength 1, span 2. Plot the shear force diagram, right? So you can do the same thing for shear. You can get axial force, torsion diagrams, whatever you want to get out of it, you can get out of it. All right. Sometimes that's not as useful as what we would like. So you can go in and you can actually right click on a member and it'll bring up this diagrams dialog box for those objects. And so this is useful because you can actually go anywhere along the length of the member and you can pick out the moment that's acting there. You can pick out the shear force. You can pick out the deflection. And we can work in units of kip feet or kip inches or whatever. And what we're looking at right now are major axis bending items. We can also look at minor axis, which should give us zeros because we're not bending it about the minor axis. We can look at axial force stuff as well. But since this is a beam in a 2-dimensional frame, then we really only have major axis stuff. And so this is kind of nice. We can type in a specific distance here, like say 45 feet. Whoops, I hit enter. And that would give us our results that way as well. So that's useful, but it's also tedious. And it's tedious because it only gives us objects. And so if we wanted the moment diagram for the entire girder, that's challenging to get. right? So it only gives me the one object. It doesn't give me all of the objects together as a girder. And so that's limiting. And that's really one of the few things that visual analysis does a little bit better than SAP 2000. You can plot graphs for all of the members at together in visual analysis. Can't do that in SAP like this. One more thing that I'll show you here is if we go to, where is it, display and show tables, you can actually export all of the results in a tabular format. In fact, this is digging a little bit deeper. You can export anything you want about this model to a table, and it's an Excel-like table. So what I'm going to do is go to joint output. I want the reaction forces. I'm going to go to element output. And so I want the element forces for the frames. I don't want the stresses, so I want the forces like that. Let's see what this gives us. Yeah, that's not what I want. And then you can go over here and select which load patterns you want to output for. You can select which load cases you want to output for. And so, yeah, selecting these 4 is appropriate. And so then what you can do is hit the OK button. It crunches for a minute. And then it gives you this dialog, which is moderately useful, but I think as soon as you start playing around with this, you're going to recognize that this is just a poor man's version of Excel. You guys all have Excel for free, so why not work in Excel when we can? One thing to note, though, is it created multiple tables for us. Down here, if we go to the, where is it? If we go up here, we have another table for joint reactions as well, right? So it has multiple tables built in here. If you go to File, and you can export current table, or you can export all tables to Excel, and then it'll crunch for a minute and it'll open up a version of Excel, an instance of Excel. Okay, see the flashing down here on the toolbar. And for reasons unknown to me, it actually creates a version of an Excel file that is older than the version that I'm using. So I'm using the latest and greatest version of Excel on my computer, but it creates an XLS file that is like for Excel 95. And I don't know why, but it's not that limiting. So you can basically go through here and you can edit all these values. And so there's a sneak peek into how to use these values a little bit more intelligently. I'm just going to close that out. Don't care for that anymore. Don't care for that anymore either. Now, in the 2 minutes I have remaining, let me show you the mistake I made. Go back here. We'll make that larger. When I defined the truckload, I should have defined the truckload with an impact factor of 1.33 and a distribution factor of 0.9643. I forgot to put those modifiers in there. I just defined it with axle loads of 32, 32, and 8. So I'm going to try something. I don't know if I can do this on the fly or not. Let's see. What we could do is we could go back in and redefine those loads if we wanted to. That's not as elegant as what I would like. So if you go in here, let's see, I think it's in Edit, Interactive Database Editing. You can go into the load definitions, let's see. Yeah, I don't use this very often. So here we go, frame assignments, frame load assignments. There we go, point loads. And I'm going to modify that. So what that does is brings up this table. So this is a table that gives me all of those values. So let me see if I can edit that. So I'm going to type in 32 times 1.33 times, what was it, 0.9643, 0.9643, hit enter. And yes, and we're golden. So I can go through and do that again. Right, and we could do the same thing, times 1.33 times 0.9643, hit enter. And so we could go through and do the same thing to all of those. Let me see if I could copy that. Yep. So I'm using Control C to copy and Control V to paste. Whoopsie. Control Z to undo. Copy that. Paste there. Paste there. Hit apply to model. And so done. Now when I go back and look at those load assignments, let's see, we'll look at live 2 and see what's on there. So Yeah, now we have values that reflect the truck axle weight plus impact plus the distribution factor. So that was a quick way of correcting that. All right, I'm out of time. That's a lot of information in a short amount of time. You guys have homework number 2 you can start working on. And so if you work on problem number 2 of homework 2, which is the SAP thing, you can kind of go back through this video recording and stop and start and kind of piece your way along. So that's it for me for today. I'll hang out for a minute or 2 to answer questions if you have them. Otherwise, I'll see you guys next on Tuesday at 12:30. Go ahead and hit me up in the meantime. I'm not doing anything terribly special over the weekend, so if you have questions, feel free to text me or email me or hit me up if you catch me on campus. All right. Otherwise, have a great holiday weekend, and I'll see you guys all on Tuesday.